is Professor Mark Thiemens. Professor Thiemens is a distinguished professor of chemistry and biochemistry in the Department of Chemistry and Biochemistry at the University of California, San Diego. I read a little bit about what Professor Thiemens is doing, and I was impressed of the spectrum, if to borrow a word from the previous lecture, of time and space and everything. Professor Thiemens will speak about the use of isotope effects to understand atmospheres and climates, present and past, and track the origin of life. Professor Thiemens, please.
Okay, so I know I'm up against time, and it's the end of the day, and I'm hungry too. So I'm going to tell you how I'm going to do the talk, and then it'll be easier to follow. So when I go through a little quicker, you won't have to worry about falling off the tracks. It's an isotope talk. I put this on for 3 reasons. To remind myself it's an isotope talk: hydrogen, deuterium, tritium. I put it on. When I came to San Diego, I inherited Harold Urey's old lab, and since he discovered deuterium, made it appropriate. And third, it's deuterium. I mean, this is Jerusalem. The book Deuteronomy was written here, so how could I not use it? Here's the theme. Okay, this part you still have to be tuned in. The oldest rocks on Earth are about 3.8 to 3.9 billion. So there's no record before that. What we don't know in the origin of life that I'm going to track, I'm going to tell you a strange mystery story, how we track the oxygen levels and how you know how much is there. That's important. How you make organic molecules, what the redox state is, how does it change over time, how do you make the oxygen, how can you tell? And people tried for doing this for decades, more than 60 years in it, I can tell. At least until 2.8, because that's when the great oxygenation event comes in and the Earth precipitates out iron oxides, and we know that happens. So we have a good idea there, but this whole zone here is important. The biological part, the world's expert on that whole system who discovered it actually is Bill Shechtman. He's sitting right there, and he'll tell you on Thursday afternoon. And so the part I will deal with is the oxygen story. Okay, so I have to do just a little bit of the nuances of isotopes so that you can understand what I'm saying, and hopefully it'll be okay from there. All right, the whole field starts, it has a birthday. It's 1947, so it's off by 1 year, but there's these key papers that Harold Urey, Bigelaisen, and Mayer wrote, all at the University of Chicago, about the thermodynamics of isotopic substances for a whole bunch of molecules and the vibrational frequencies and the temperature dependencies of them for different molecules. So they were classical papers. But they didn't do any good if you couldn't measure these small differences in isotope effects. But it just so happens a guy named Al Neer came along after World War II and his role in the Manhattan Project, working with Fermi on finding fission yields, developed the isotope ratio mass spectrometer. And it all happened all in 1 year, and it all goes from there. We'll look at isotope ratios, because like anything, you can measure a ratio better than anything else. So we'll measure the 17 to 16 and the 18 to 16, normalized to the most abundant isotope. Okay, and measure the ratio of it. We'll do the same for sulfur. Okay. So a use of it, this is the one thing. So when Urey calculated this, I'll say it this way. We all know about climate change. Probably everyone in the room maybe believes that the Earth is warming. But the way you want to prove it, things like glaciation and all that happens, is you have to know the temperature. How do you know the temperature more than, say, 100 years ago? What do you measure? The only way you get it is from the isotope record. And it goes back to Urey's table. If you want to do it at longer time scales, you can measure these little critters called Foraminifera. They're carbonate shells that grow in the ocean. They die, they fall to the bottom of the ocean because they can't fly. And then you can drill and you measure them for the oxygen isotopes. You know the oxygen isotopic composition of the ocean at the time, which is, there's a story behind that, but you do. So the isotope exchange from them, you just look it up and or measure the calibration curve, and it gives you the temperature to 1/10 of a degree centigrade, millions of years ago. You can see the glaciations and the interglaciations, the glaciations. You know that we're supposed to be heading into a glacier period now, and you know it from the isotope record. There would be no discussion of climate change without it. So there's a lot of fun stuff you can do. We use a funny notion, but basically we measure these things in parts per thousand, which is what this is, but it's the 18:16 ratio and 17:16 ratio. That's all you have to know, because this is the high-speed pre-dinner program. So when you measure the oxygen 17:16 and the 18:16 ratio, and you measure everything on the Earth and the Moon, you normalize ocean water so we can compare our measurements around the world. You have a standard. And you measure the rocks of the Earth, you measure the rocks of the Moon, you measure water in the atmosphere, which is depleted in the heavy isotopes, you measure carbon dioxide, you measure people. We live somewhere down in here in the water in our hair, in our bodies. Everything lies on this straight line. Slope is 1/2. Mass difference of 1, mass difference of 2. And all the rules depend on mass, whether it's vibrational frequencies. You're a physical chemist, you know this, but vibrational frequencies, diffusion, vapor pressure, all depend on mass. The one exception was this. There was calcium aluminum inclusions from a meteorite that Bob Clayton measured, and this started the field of cosmochemistry off and running because oxygen is the main element in a planet. It's half of the planet. And there was a big isotope effect in these inclusions that were interesting because they predate the formation of the solar system, and it lies along a slope 1 line. And so the whole community realized this must be nuclear because you can't get off of this line by anything chemical. So this is pure oxygen 16 coming into the solar system from outside the solar system, coming in as a crystal, trapping in these calcium aluminum inclusions. And so this is supernova debris. That's how you make oxygen 16. All right, so it was all based on that assumption. All right, now we get towards to where we're going to need things. And then the first little experiment I did as an assistant professor in 1983 at the age of 8, I started with a sample of oxygen, made ozone, measured the residual oxygen, and it's exactly a slope of 1. It's exactly the same as the meteorites. No ifs, ands, or buts in it. The only time I knew the measurements were right, that was for sure, and there was no supernova. That was for sure. But it seemed as though that's so clean it will be easy. So the fact of the matter is, where does it come from? Well, you know ozone is formed. It's pretty simple. If you look at it this way, dissociate oxygen, form an intermediate either quenches and goes here, or it falls back apart again into an oxygen atom molecule. That's all there is. So it should be easy. So I worked for years to try to find my way to understand it. A lot of people did. Sir David Bates worked on it. Dick Zare worked on it. A number of other people, Jürgen Troll worked on it a while. And you will be shocked to know that the one guy who figured it out was Rudy Marcus with his colleagues, Gao and Hawthorne, have written a series of papers. I like this one the best because of the title about being strange and unconventional. One of Rudy's colleagues at Caltech said to me, he said, Mark, when he says strange and unconventional, was he talking about ozone or was he talking about you? And I told him, no, I'm sure it's ozone. So I don't have enough time to do it, and it would be crazy for me to try to explain it because the guy who did it is sitting like 20 feet away. But one of the parts in the transition state that comes in, there's factors that you don't normally worry about that Rudy picked up and included into a long master equation. And part of it is that the symmetry effects are important because of the symmetry effect, and you have different state densities. So he included the state densities into it and showed that they're important. And ozone in the experiments preferentially enriches this in the product. So part of it is this number of state densities. Part of it's the density. Part of it is the coupling to the states channel and a lot of the other things. But the important thing Rudy gets out of it is that he explains some of the experimental data. The rate constants for the even ones, if you normalize it a pure one, the purely symmetric ones sort of do what you might expect. But the ones that are asymmetric, I can't remember which one's which. One is the experiment and one's Rudy's calculation. So he gets it all right. That's pretty impressive. No one even came close to dealing with how to explain these in a way that was physically, chemically believable. The other, and I don't have a plot of it, is the pressure drop-off. We measured it out to 90 atmospheres, and it falls off faster than you would expect based on a Lindemann-type reaction. And Rudy got the pressure part of it right, too. The only thing we don't know, and we're going to come back to this, on the origin of life, is how to predict it for other molecules. And to get the magnitude of the effect for the overall, starting from a normal composition, getting that exactly right is a hard job. Okay, so I'm not going to talk about this. This is about, in the interest of time, it's the part about the early solar system. But one of the parts of the older system in models, one of the models that people thought of had to do with photodissociation of carbon monoxide. So we did experiments on carbon monoxide photodissociation to see if they agreed with the models, and it didn't. And they were all unhappy with it. We published it, put it in Science, tested everything we thought was testable. They still were unhappy. So I decided, I've got to do this right. I need to get some help in the photodissociation. So I asked my friends if they would introduce me, in a talk over at Hebrew University, if they would introduce me to Raphael Levine. And I'd see if I could get a little bit of his time, because I need to talk to him. Because as far as I can tell, he's the only guy that will really be able to answer the dissociation part of these experiments that we've done and get it right. So they did, and I was lucky, and it really worked out well. And Rudy and his colleagues have tutored me. That's also true. Rafi and his group have tutored me, and we've written some work together, and it's been very nice. So the experiments we did at the synchrotron up in the People's Republic of Berkeley, and you have to do them in a short UV, so you can't have a window on your system, so that makes it really a pain in the neck. And you have to collect everything to take it back and measure it. And so we built the whole system. We did the carbon monoxides, and we're done. When I talked to Rudy, Rudy said, look, forget about carbon monoxide because you don't know everything in the excited states. You don't know the isotope lines. They're not measured. Do nitrogen. It's isoelectronic. So we did. We rebuilt the chamber and did nitrogen, and Rafi modeled it, found ways to test it to see where the action is. And in this paper, we all worked together on, in 2011, what Rafi and his colleagues and Harel Muscatel found is that when you worry about all of the Rydberg and valence states, they all couple. You have to get all of that in part of the picture. But it's worse than that. You have to do it at the isotope level. Second, and then you have to cross the surfaces and eventually dissociate. And they calculated all that. And you have to do it at the minute level of coupling between the states, and they did it. And the part that shows that is number one, the action is in here where the states are very clustered. They're perturbed. And so Rafi suggested one winter day when we were sitting in his office, go to this wavelength because this is the most congestion. And we found that that's right. The biggest variation was exactly where he said it would be. And so he wrote it up in this paper. But the other part of it that's fundamental is that if you calculate the isotope effect from dissociation, this is what you calculate from the cross-sections. Just put it in a box, dissociate it, collect the products, count them. And this is what you get. But this is what you measure. There's a lot of people in the world do photodissociation calculations for isotopes. And so this is what the difference is. There's a paper coming out. I just looked. It's in PNASA Ahead of Press that Rafi and his colleagues have written. Sorry, it's right here. And Dr. Komarova is sitting up there, and she's a co-author on this. This is a beautiful paper. They've done the quantum dynamics of it. And it really gives you the last part of this problem. And I don't want to spoil the show, so you have to ask Rafi and them, because they should talk about it, because I didn't do that one. So now to get close to what we measure, we look at the 34, 32, 33, 32, 36, 32. And we worry about the mass dependence part. And there's a term that we'll use, which normal is here. This delta term is the deviation in the 36 and the 33. All you have to know is if it's normal, it's 0. If it's anomalous, something's going on. Okay. So now we're going to chase the rabbit down the hole. So this is where it's going to, this is where it gets weird. So everyone knows you don't chase the white rabbit down the hole because bad things happen. So the story starts on the surface of Mars. We measured sulfur isotopes in a Martian meteorite. I won't tell you how we know they're from Mars, but even the community doesn't argue about it. What we wanted to do was understand the oxygen in things that sulfates and carbonates because they're made from water. And the big mystery on Mars is where did the water on Mars go? Because if you want to understand the origin of life, you have to understand water on Mars. So we measured the carbonates and sulfates, and it worked. And we got the numbers, and we did a series of papers in Science and Nature on this, and we can do it over billions of years. But the sulfur was anomalous. Not by a lot. It doesn't seem like a lot, but we spent 10 years to get the chemistry to where we could do 10 times smaller than this. So it's anomalous. But it was easy to figure out what it could do. Mars is simple. So it could only come from sulfur dioxide photolysis. And it does it in the UV region. That's plain and simple. Photochemists have known this for, I don't know, at least 50 years. And it makes oxygen and sulfur. Sulfur oxide and oxygen. So we measured, you can't calculate it. So we measured it. And if you measure it, you get these anomalies. You start with a gas at 0, 0, and as a function of wavelength, you get some that are positive and a residual that's negative. That's what we see in the Mars samples. Okay, forget Mars. It's interesting, we can talk over a wine, but forget Mars for now. Today, sulfur dioxide only gets a couple kilometers up, and then it washes out. Lifetime is 4 to 5 days in the atmosphere. It's soluble, right? You're chemists. And so it doesn't last long. So it never gets up to where the UV light is to get this isotope effect. Okay, fine. So then we thought from there that, well, that's all right. We don't expect this in the atmosphere today because the UV light is up here. And this is the ozone layer. That's what screens out the UV light. UV light, where the photolysis of SO2 should occur like it does on Mars, it's all up here. And not at this level here is where the SO2 is. So it never sees it. Okay, fine. So what? Doesn't mean anything. So we were doing the thought experiment. What if there was no oxygen in the Earth's atmosphere? If there's no oxygen in the atmosphere, there's no ozone. Okay. If that's the case, the UV light comes at ground level. Okay, so what? Yeah, but we want to know, in the Earth's early atmosphere, was there any oxygen? Because if you looked in the literature 15, 20 years ago, it varied by what? 6 orders of magnitude in the models. Some of them said it was 0, and some of them said it was the same then as it is now. But you have to know this if you want to start making organic life, what the oxidation state is. Can you burn up? Do the molecules burn up, or are they safe? Do they have to go underwater or above water? So we thought, all right, well, that's easy. So what we'll do is, and James Farquhar was the fellow in the lab with me, and he was a real geologist, and I'm just a voyeur. Went to people like Bill that know this by scratch to get samples of all the oldest rocks in the world. All the billions of years one. Just asked. Geologists are great. You know, it's like baseball cards used to be in the United States. We trade them, you know. Hey, do you have a sample of this? Yeah, man, I'll buy it for you. I'll give it to you. But if it's better than meteorites, because then you talk to the curators and you have dinner, and they say, can I have a sample of Allende? They say, well, I don't know. When we go to dinner and talk about it, it means it's going to be like a $100 dinner because of $20 of food and $80 of wine, and then you get the meteorite. But the geologists are better because they want to get rid of their rocks because then they have to go in the field and get more. So we got samples to look for. So this is simple. The capital delta should be 0 if it's like today. But if there's a signal, it means the ozone layer isn't protecting it. Okay, so we'll cut right to it. Here's the capital delta. Here's normal, 0. Here's today. Geologists, 0 is today. That's not a triplet singlet state, a delta state, by the way. I don't know what the heck that is there for. Here's the great oxygenation event. But look, here's the Archean. It's all anomalous. There's sulfides and sulfates, so you have negative and positive, and it's large anomalies. And there's variation in it. So we can calculate how much ozone is there. It's a Beers-Lambert law calculation from here. You have a column, and how much oxygen can you tolerate until this goes away? That's all you have to do, and so we did. But I'll point out there's other things we want to learn about. There's structure. It's what they called whiffs of oxygen. Are these false starts? Are these places where life came in and it decreased the signal? Or is it just the geologic record? Or was there a big loss of oxygen here that the signal got bigger and then we got the whole atmosphere up and running here? It's possible to know. We've got some chance now because we can go with this mineral by mineral with techniques today and separate out the species and start answering this. But there's always a but. There's things we have to know, and there's some changes now. But I say we did the calculation, putting S2 on the SO2 is how much oxygen could you have and still get the signal. About 1,000 times less oxygen than now, and you can still have the signal. You can go less than that, but you can't go more than that. So it's a hard and fast number to live with. Okay, so you get it out of this. Okay, so now I'm going to tell you some things. So take some chances here. So I always thought, if this elephant can tightrope across this damn canyon, we could take a few chances here and there. I like this picture. This is an advertisement in science for something like centrifuges, I don't know. So, next is our field work. This is, see, now you have to pay attention because you say, what the heck is he going to talk about now? So this is the South Pole. That's the South Pole. That's 90.00. And that's last year's South Pole, and that's the 1 year before. It's 2 miles of ice, and it moves about 10 meters a year. So, and the temperature is, it's just what you would expect it to be. It's awful. And so we went there to get a time record, year by year, going back 20 years. So we look at the fine structure at the isotope level of particles that are chemically transformed coming into the South Pole, because it's a long path for chemical transformation. It's the longest path you have, is getting to the place. So we did. The problem is you need a lot of sample. Well, what's the big deal? You got to dig it by hand. So this is a picture. I remember when they took this picture of me down at the bottom of this, there's a shovel down there where you just carve it out. And I was thinking, man, in fact, I thought of Rudy at the time. I said, why wasn't I a theoretician? But then I got home and I thought, that's because I'm not smart enough. And so I still had to. So we dug out and took samples year by year, and also little subsamples to measure the trace species. Bagged them all up, took 20 tons of this to the National Ice Core Laboratory in Colorado, transported them back to UCSD, and measured the isotopes. That's it. So here's the result. I'll just walk you through it since we don't have a lot of time. Here's the normal. So everybody should be normal in the sulfate. Sulfate gets oxidized by ozone or OH. And here's the time, 1983, 2002. And what you see, this red one is an El Nino index. This is a measure of the change of the Pacific Ocean and circulation on the planet. Okay, but it's when the Western Pacific warms and it extends over as far as California. And you get big climate perturbations. In California, we get a lot of rain. So my fellow Californians know about El Ninos. So we had El Nino years, and that might have perturbed it. See, here's one here, here's one here, and here's one here. And you get changes in nearly the same time period, or the big ones in El Nino years. But somebody pulled a bad stunt here. And this year, here's Pinatubo, and here's El Chichon. It's a volcano. Volcanoes, the big ones put SO2 into the atmosphere, and there we go. It's our experiment in the lab. SO2 photolyzes. And so at least we can check how the anomaly gets made by UV photolysis on Earth, because the volcanoes did it for us. So since we like the South Pole so much, we did the same thing in the Greenland summit for 6 weeks. And got the same results because the volcanoes go north and south, and we got to live in a tent some more. But we got lucky here. The biggest signal, and there's no volcano. It's not an ocean effect. What is it? And so we thought about it a while, but then we remembered this El Nino was the biggest El Nino in recorded history. It's also the largest monsoon in recorded history. And what happens after an El Nino, it goes away, but then there's a year after, it's called La Nina. And during a La Nina, it changes the circulation patterns and the earth gets cold and dry. And if you're from the places like California, when it gets dry, it means it's fire season. And especially if you get more high pressure areas out over Nevada, which gives us what we call it gives us the Santa Ana winds. So it's hot and dry, and that's when you see us in the newspapers between, say, November and February, is we get fires. And so that happened to be the biggest wildfire in recorded history on the planet of the Earth. In atmospheric chemistry, atmospheric chemists are like all scientists. They don't agree with anyone about anything. But the one thing they agree on for recording a climate for burning is potassium. So there's the year, and there's potassium. It's biomass burning. And here's another El Nino year. Volcanoes don't emit potassium. Cars don't emit potassium. In atmospheric chemistry, if you have a balanced budget for a greenhouse gas and you don't know what it is, then you blame it on the cows. As far as I know, cows don't do anything to potassium, but I'm not interested enough to find out. So it's burning. So what happens is, and we've modeled this, but the long and the short of it is, in the equator, SO2, in that burning, in that convection zone, goes straight into the stratosphere, along with carbonyl sulfide, which is a burning product, which gets up higher into the atmosphere and converts to SO2. So the SO2 gets up here, and it's like Mars. It's right in the UV light that gives you the photochemistry effect. And the SO2 converts to sulfate and drops into here. When we follow the volcano plumes, when we get a very high resolution snow pit, which means an extra month in a tent in some place, you can see the evolution of the SO2 at the isotope level. So we get a really good feel for how this occurs in nature, and that's good. So that was really useful. And those samples in the snow pit, and that stupid snow pit, are this, and these are all the early Earth samples. So the SO2 part sits in with the Archean part, the Precambrian part. It looks like SO2 photolysis. Fine, let's quit. Let's go home. Okay. As I said, there's always a but. So I got involved with something else, and good, I'm right on pace. I was interested in Tibet. This is the Himalayas. The Himalayas, and this is the Tibetan Plateau. Here's what I got interested in and why. Number one, this water region of these glaciers is the only water source for little populations like India, Pakistan, Bangladesh, Vietnam, oh, and by the way, in China. It's more than 2 billion people get their drinking water from this, and it's melting. But you can't get the melting rate right because you can only get in there between, say, April and June, because before April, it's winter. You don't go anywhere in Tibet in the winter. Just forget it. You can't, especially here. You can go to some of the places on the northern plateau, but you can't get up to here where you want to look at melting rates. And then by June, the end of June, forget it. You can't get in there because it's monsoon season. So you can only go in there part of the year. So it's hard to measure the rates. And it's a little hard to get to. And so, and there's not things that you can directly measure. So I thought of a trick. It's always fun to think of tricks. The trick is this. Something I hadn't done before, but I thought it was time I tried it out. Everyone knows about carbon-14. So it works the same way. You have a supernova. Before you ask, it's a type 1 supernova, not the type 2, because they're more abundant in the right energy range. So it's between 10 billion electron volts and 10 to the 21st electron volts. Comes into the top of the atmosphere, collides with argon-40, spallation reaction makes radioactive sulfur-35. The clock starts. You make sulfur-35, click, click, click. Chemically, calculate the oxidation rate to SO2, about a millisecond, maybe 5 milliseconds, who cares? But it's 3 to 5, and the problems of rate constants aren't normal. That's the accuracy of the rate constant. So now you have a radioactive gas. That's good. And it converts to a solid, even better. So that's one of the reasons to get the gas to particle conversion time. There's no direct way to do it. So that gives you a clock. But here's the thing. If you want a clock in ice, you need something on the right half-life. Carbon-14 doesn't help you at all. It's 5,700 years. It's too long. Tritium's no good. It comes in with water and it loses its process. Then there's things like lithium and sodium, and they're hard to measure, and they're the wrong half-life, and they behave badly in the atmosphere. But 87 days, it's Fat City. It's right where it should be. So we decided to go and measure it in the ice in places over the course of the last few years. So last year, almost exactly this time, I took this picture. So here's the people for scale. And we collected ice here. That's Mount Everest. So it's not all the way up. None of us summited it, but we went further than it's comfortable. I grew up in Miami. This is not my kind of place. And it looks like it should be cold. It's really cold. And so we collected ice on these in the glaciers, and then the runoff from the regions. That's Mount Everest, and this is Rongbuk, where the temple is, the Buddhist temple, the highest Buddhist temple in the world. And so you measure the radioactivity in the air, you got the clock. Measure the radioactivity in here, you got a little bit slower clock because of the difference in time to get here. And then the melting rate comes when you measure the runoff. But the best part of this is that you only have to have a liter or two of water because you're measuring a radioactivity. You don't have to measure all the water. You only need to know the activity. And you can count almost individual atoms with the way we've developed it, so it's good. And so we wanted to get glaciers too. And here's another glacier. This one's only at 18,000 feet. You have to climb. This is the base floor. The base floor of this part of Tibet is at 16,000 feet. So that's the low level. This is the flatlands down here. So, and there's no way to get here. You have to choose your colleagues wisely to do this. And I will show you a picture of the best colleague you need when you do this. And it's not this guy. This guy's expendable. But the yak. This was a low-budget operation. It was a one-yak operation. So I got one yak, and so here we're choosing it. I let the pros do it, though. However, I did buy a yak. If you ever need a yak in Tibet, call me. I can get a deal for you. I know a guy. Okay, so here's what we found. And this is going to close out, and I'll be just about on right for happy hour. Here's the sulfur-35 activity. If it has more, it's more stratosphere. If it has less, no stratosphere. So more stratosphere, which is where SO2 would photolyze, higher activity. So here's the radioactivity of sulfur-30, the stable isotope, and look at that. That's not bad. In this day and age, and looking at that size of an effect, that's not a bad correlation. It's pretty good. And so the sulfur-33 is correlated with sulfur-35. The anomaly is coming from the stratosphere. It's SO2. Yay, I got what I wanted. But then you measure sulfur-36, and look at this mess. Yeah, I know. I won't say what I said when I saw it. But if you look at the concentration of sulfate, this is what the atmospheric chemistry people use. This is high sulfate from pollution. Or you can measure this molecule, it's apparently a saccharide. You only make it in biomass burning. I couldn't draw you the structure. I don't believe in molecules that have more than 3 atoms, so I don't. But this is a biomass measure, and look at this. It doesn't correlate with, it's biomass burning. I mean, it's just simple. That's what it is. It's biomass burning. I don't know what the heck's going on there. So now, but we know how you get an anomaly. It means it's more complicated, at least here, than we thought. And these samples also fit in with the Archean rocks. And it's this. Remember O plus O2 with the Rudy Marcus mechanism. In biomass burning, you get S2 plus S2, you get HS plus H, SH plus SH. These happen in combustion. These are well known. The JPL has a published book on rate constants, and you can look these up. But these are symmetry. S plus S2, it's basically O plus O2. So you have a chemical reaction in the plumes that produces the sulfur-33. In the Archean, you don't have plumes from biomass burning, but you get these same reactions in volcanoes, which you do have. So what you have is two different signals going on, but now if we can know enough about these sorts of reactions, and we know from a paper we did to test symmetry effects in sulfur, you do get them. So we have to now know a little bit more about this, but at the end of the day, we can understand the Archean better. So now we have two different contributors, and I know what you're thinking. I'll just go back, because this is my next slide. It's not a confusion, it's a conclusion slide. Is that, well, don't you get since this comes from SO2 photolysis, Mark, your experiment showed you get a sulfur 33 effect. You do. But you can see that you also get a 36 effect, but the signal that's is stronger from the biomass for an anomaly at 36. So it means that you can peel them apart, but we have to know more now about those sort of processes, and we can understand more about the early Archean atmosphere and the contribution to the species. Because now we'll get a better fix on the gases being emitted. We'll have a better fix on the contributors that are in the atmosphere at the time of the Archean. And so that's basically what my conclusion slide is. I always put a lot of detail in my concluding comment slides. So this started with this anomaly. Where we need to go in the case of ozone, as I said, well, the last part we want to be able to do is to get the magnitude of the effect. But to understand the Archean, now we need to know it for other molecules. We need to know more about the SO2 because that has a wavelength dependence, because we know from Raphael's work that dissociation is a very wavelength dependent effect. And you can barely calculate it for something like N2, and it's really hard. Raphael's just about got that wrapped up. When you see his next paper, you'll see it's getting close to a full picture. But a triatomic, forget it. You can't do it. And so that's what needs to be done. But I have to leave you with, I'll say, here's a grand challenge slide. This is for Raphael. Figured I had to do something. So when I was here, not so long ago, you saw the places I went to. And you do the math and you look at them, you say, man, you got to stop going to Mount Everest and Tibet and South Pole. I'm tired of it. I'm just really, really tired of having to get samples to go to cold places and places where I can't breathe and sleeping in a tent. I've just had enough. And I got so fed up with it, I had to come up with a way to get samples without doing that. So when I was here, 7 or 8 years ago, I went out to Masada to test out a new machine in a cistern in Masada. And so what I came up with was a way to do time travel. This is my first experiment. You can see the beam being beamed up. I choose my time. I can go back in the past and I go up in the future. So I can do the time travel part. So that's the future. And so the reason I did this was that early this morning, I went ahead 100 years to here, came in to see if there's having this conference in the future, in the anniversary of Israel, and they are. And they were still talking about this one and how good it was and how they have to try to keep the pace up 100 years from now from doing it, because Raphael made it so nice. The tradition is still there. So Raphael, I can tell you, their colleagues in the future thought really highly of you. And so that's what my contribution to the grand challenge is. And if you want the details, forget it. I'm not at liberty to talk about it. And thank you for inviting me here. 5 minutes here. I only got 5 minutes. He scared me. He said, I got to finish or he'll kill me.
Yes.
One small remark, Mark. Mark.
That's triple.
I like your stuff on the Archean. I just wanted to mention that last fall in Precambrian research, I had a paper from the Archean at 3.4 billion in Western Australia. But what's interesting about it, I rather like problems where you can attack it from a couple of different angles. This is microbiology and fossils.
Yep.
And it turns out that there is a mudflat community of photosynthetic bacteria and sulfate-reducing bacteria. And the sulfate reducers are producing H2S. The H2S is powering non-oxygen-producing photosynthesis. It is in an environment in which both of these groups are obligately anaerobic, and it's exactly what you would expect. And so the paper says there ain't no oxygen there, which is exactly what you are saying.
Yeah, well, that's good. Thanks, Bill. I'll get the reference from you later so I can look at it. I missed it.
No.
Precambrian. Okay.
I have a question. My life is, for the last 40 years, is focused on sulfides.
Okay.
And I always tell my students that oxygen is our biggest enemy in the world because we work on cogonites. And the trouble with oxygen is that all the oxides are higher valency than the sulfides, and they are more stable than the sulfides. So we have to fight really the oxides in every way that we can. And I wonder, if I would live 500 million years ago, would it be for me easier to go and work on sulfides and produce my lovely nanoparticles rather than today?
No, it won't be any different. I mean, I can get you there if you want to go 500 years back, but no, the oxygen in the atmosphere, you can tell from the ice core record and the bubbles that it's anything in the ice core that you can measure through the Holocene. There's some variations in it, but it's just from primary productivity. It's tiny. No, you're out of luck. You have to go much further. And even from my machine, you'd have to go back. You'd have to at least go back more than 800 million.